All right, guys, we'll start now. So, welcome back, guys, to CSF 425 Deep Learning. This is lab session number 2, and we're going to continue from where we left last time. In today's lab session, what we're going to cover is we're going to first complete some of our work from our logistic regression model. We're going to extend the logistic regression model into a neural network. So we'll learn what a neural network is and some basic neural network stuff. In machine learning or in deep learning lingo, it's called multi-layer perceptron. So we're going to learn about that. I'm sure you guys have introduced that to yourselves. I mean, like in the lecture classes. And we'll also introduce ourselves to a little bit of convolutional neural networks, which is a variant of neural networks. So let's get started, shall we? Um, All right. So before we start, I hope all of you have opened your notebook from last time. And let's actually just run the entire logistic regression stuff because, I mean, we're going to need to continue that. So I'm going to first need you to check if your runtime, if your, nothing. Never mind. So let's just run this. Uh, and it's going to first ask me to upload my kaggle.json file. I hope you guys have not deleted that file. If you have, then I'll ask you to download a new file from kaggle.com, and I showed you how last time. Uh, okay, I need to copy the code. So first, you guys need to run the code where we uploaded the kaggle.json file, which is this one. I'll just copy paste it over here. And you also need to relocate that file to a particular location, which is root/.kaggle, which is where kaggle.com expects to find that kaggle.json file. It won't work in any other location, so you need to make sure that your kaggle.json file is in that. So I'm going to write the code for that. Where is that? Yep. Right. Let me just run this. Okay, I think I've deleted the file too, so let me just download it with you guys. Follow me. If you have the file, just upload it. If not, I'll just download it really quick. You go here, you go to account, you go to API, and you do create new API token. One more, guys. One more thing, guys. I'm actually traveling this week, so I'm actually coming back to Plani. So I don't have my dual monitor right now, so I can't really go back to the chat again and again. I'd really appreciate if you guys can just open your mic and speak up. That'll just be really helpful. Or I'll keep checking it in between, but I won't be able to reply like ASAP. So that's that. Uh, and what do you yes, the license file. So I have it over here. Let me just upload it really quick now. And let's actually just run whatever we ran till now, right? I mean, you guys must have already written those pieces of code. Oh, let me just share this file again in case you guys have lost it. I'll just share this file with you guys. So you can check over here, like in case you fall behind or you think that you don't understand something, you need to go back to something. So, and I'm gonna paste it on the chat. Oh, it says name PD is not defined, so I need to import that. I think I should import everything at the top. I'll just type it out fresh. That's okay. So I need import pandas as PD. Yep. Right. Okay. Torch is not defined, so I'll import torch. Import torch. Right. Init param. So here we initialize some parameters using a random function in torch, PyTorch. And that goes through something known as required grad, which means that you tell PyTorch to keep track of those operations so that it can calculate the gradients on its own. We covered this last time. All right, so where we left last time was this definition of a logistic regression model, which is nothing but a simple linear model, right? Y is equal to mx plus c, but it is passed through a function, a non-linear function, which is this torch dot sigmoid, right? And this sigmoid function looks like this. Right? This is what it looks like. It I mean, this sort of curve that goes from 0 to 1, and anything if x is less than 0, you get a value that is less than 0.5, and if x is greater than 0, you get a value greater than 0.5 but less than 1 always. It asymptotes at x is equal to, or y is equal to 1. So what essentially a problem over here is that suppose we want to do some classification and there are two classes. Our problem is essentially to find those weights and that bias that will give you that when you do x times weight plus bias, it will give you a negative value for one class and positive value for the other class, which means that when you pass it through torch or sigmoid, you either get a value less than 0.5 or greater than 0.5. And so what we can do after that is simply say that if the prediction is greater than 0.5, you tell me that this is of some particular class number 1. And if it's less, and if the final result is less than 0.5, I can say with that much surety that my model prediction is class number 0 or whatever. All right. I told that I'll explain this at operator at one point, so I'll do that right now. At is actually a Python operator, and this was introduced back in Python 2.8 or 2.9, I think. And it's essentially just a matrix multiplication operation. So X is a matrix, right? It's a 2D array of rows, each row representing an individual data point and each column representing a feature. Weights is also technically a matrix, right? Because it's a, I don't know what, like a five, sorry, it's a 5 times 1 matrix, right? And so when you do an add operation, it will basically do that matrix multiplication using whatever rules you've learned in your calculus class. And bias is also, okay, let's see what you actually get. So x, let's see what the dimensions of x is. What's my x, by the way? It's x train, right? So let's see what x train is. X train dot shape. So it's 5 times 147, right? Yep. So I think this is inverted, but it's 147 rows and 5 columns, 5 features. Weight, on the other hand, is 5 times 1, which is like 5 features and 5 columns. So when you do matrix multiplication, you get 147 times 1. right? So you get a 147 times. NumPy actually you get those dimensions inverted. So, but that doesn't matter. Like when you do find your final operations, they get. I mean, the art operator actually takes care of that. So plus you're gonna add a bias which is of the shape 1 times 1, and here is where something magical happens. Uh, PyTorch will basically see that this dimension and this dimension is the same. But this dimension and this dimension is not the same. So how do you add those two things? So what it will do is that PyTorch will simply copy this dimension 147 times. And so the same value will get 147 times. And so this concept is called, let me just, this concept is called broadcasting, right? So we'll probably look at it in more depth when we go ahead, but just here is some basic idea for you. So that was our logistic regression model. So let's see what we got to do next. Now we've defined a logistic regression model. So we have not, we'll train it later on, but let's just see like how you get actually results from. So this is essentially a function which takes x as a value, x as input, and it gives y or the prediction as the answer. So we're gonna get simply prediction uh, is equal to logistic regression model x train x. Have I defined anything? Okay, let's do. Okay, so we would be passing the entire data set. We talked about something as batches last time, if you guys remember. Do you guys remember what batches are? All right, so yeah. So I'll just give you a quick recap. Batches are nothing but like your data which is divided into smaller chunks. Because usually computers can't handle all of the data at once. Sometimes you're talking about millions of data points at once. So we talked about what is a data loader, and basically it's the data loader's job to break that data into different parts. So if you do, let's just do one thing and let's just actually take out one batch from our data loaders. So what was our data loader's name? It's train DL. Remember that everything that is related to training must be another training data set, and the testing data set should not be touched during training. Uh, so here is a good piece of code that you should know that is next iter, and you pass in an iterator that is train DL. So if you remember, you go for x, y in train DL. So when you do anything in train in something, it basically means that that thing is an iterator. You can iterate through that. So just to avoid this line of code, you can do something known as next iter train DL. So first it will convert it into an iterable object, and then it will basically go to the first occurrence of whatever is in that iterator. So that is that. Let me just name this X batch because X is for something else. And let me just pass in the X batch into this, and I'll see that I'll be getting some predictions, and let's see what that shape is. Just for comparison, and I'm also going to be passing in the shape of my batches. My batch. Right. Okay. Sorry, I was wrong. So I think I need to do one thing. So this is wrong, by the way, because my data is formatted wrong. You see, it says that weights are not compatible. I'll tell you why. Because your x is like what? X is of the shape 5,147. But by convention, your data should come at the sorry, your column should come at the last index, and your data should come. Your data point should come at the index before that. So that is because, like, in conventionally, each row represents what you call a separate data point, and each column represents a feature of the data points. So if rows were to represent data, then your size of that of this training tensor should have been 147 times 5 and not 5 times 147. So for that, actually, I think I need to just um, I need to change the dimension. I need to like transpose the data frame itself, because my data frame itself was formatted like this. I think so. Let's just check. Uh, let's just check the shape of these tensors. I'm not exactly sure. So we'll debug it on the functions. Right. So it needs to be 147 times 5. So I'll just go to this function, and I'll return the transpose of this tensor. I think that'll be good. So I need to do a torch. All right, let's go with this torch. Torch transpose of a matrix. So you do a torch dot transpose. Let's see. Torch transpose. Oh, okay. Here's a mistake. Okay. I'll just remove this for a second. Did you guys write this last time, or did I explain this last time? Why did I permute? No, so, oh. No. I'm sorry, Chris. Anyways. There's no lag. It was my mistake. Anyways, sorry for the confusion. I'll come back. I'll come to one question. Prabhav, I'll again iterate this once more. If you guys can just speak up, open your mic anytime, that'll just be really helpful for me. I don't have two screens right now. Um, right. So, uh, so my X train over here was of the shape 5 times 147, and I need to transpose these dimensions. So in any tensor, what you can essentially do is you can use a function that is known as permute. Right? And what permute does is it can transpose
Sir, just to confirm, are you on the screen where like notebook is shown, or are you on the PyTorch website?
So can you now see the PyTorch website?
Oh, we can see the PyTorch website. I thought you were on the Colab notebook.
Oh, no. I'm sorry. No, that was my mistake. I'll just cut it out. Sorry.
Okay.
So can you now see my collab screen?
Yes.
All right. Yeah. We were over here, by the way. So the problem that I was facing was that my X train was of the same shape 5 times 147, and my weights are of the shape 5 times 1, but you can't multiply 5 times 147 with 5 times 1. You can multiply 147 times 5 with 5 times 1, because like that. So if you remember the law of matrix multiplication, right? The last dimension of the first matrix and the first dimension of the second matrix should be the same in order for matrix multiplication to happen. So that is why I was getting this over here. Size mismatch. Got 5. Got 5 times 147 multiplied by 5 times something. Right? So that was the problem. So what I can do is that when I'm actually, so here is this function that I use to actually get my data points from the data frame into tensors, into arrays, right? And here is where I'm returning it. So all I need to do over here is that I need to get a transpose of this matrix. Do you guys understand me? So for that, there's a function known as permute, which can basically permute the dimensions, according to whatever you want. So ideally, the dimensions go as 0, 1, 2, 3, right? So this is dimension number 0, by the way. It goes in the reverse order, by the way. 0 and 1, right? Is there a um, I'll answer Prabhav's question, but I'll again iterate, guys. Please open your mic whenever you want. I'll not be able to look at the chat again and again. So, is there a method which figures this out on its own? You need to, I mean, technically no. You need to like specify at least something. You need to give at least some hint to the system that this is what you want to do. So that's there. Let me just follow me over here. And what do you need to, so the dimensions go as 0, 1, but what you need to do over here is you need to reverse them. So I'm telling PyTorch over here that I want my dimensions in the order that first I will get the first dimension, the original first dimension, and then I will get the 0th dimension. So let's just see what I get from here. Yep, I think it's fine now. So I've gotten correct dimensions over here. And let me just run all this from here. I hopefully get, yeah, okay. So I get some results. So I divided my data into batches of size 16, right? So each data will have 16 rows and 5 columns, and I got a result which is of 16 values, which basically tells me a value between 0 and 1. So, and what I need to do now is that wherever the value is greater than zero point 0.5, I can predict confidently that the prediction of the model at that point is a 1. Uh, and if it's less than 0, I can say that it's 0. If someone's writing on the chat, can you please open your mic and speak, please? You don't need to raise your hand. You can just simply open your mic. I don't know. There's something?
Sir, can you please explain again how you removed the size mismatch error?
Right. No issues. By the way, you guys can call me Palash. That's not an issue. So let's just. So do you remember what issue we were having? Basically, my data was of the shape 5 times 147.
Yes.
Yeah.
Yeah.
And my weights are of the shape 5 times 1, because like corresponding to each feature, there is a corresponding weight, right?
Hmm.
Yes. So I couldn't multiply 5 times 147 with 5 times 1. Yeah. So I need to
Yeah.
transpose that X matrix to from 5 times 147 to 147 times 5. Yeah.
Okay. Okay.
And that makes sense because like conventionally what how we represent data is that each row, which is basically the dimension number, I mean the left dimension, right? uh, that is that corresponds to the rows. Each row corresponds to an individual data point, and each column represents a feature. So it makes sense to transpose my X matrix, right? So I just went and saw where I was actually deriving my X arrays. So I found out that here was a function where I actually was deriving my X values. So uh, till this point, I only had a data frame, and over here is where I actually derived my x's and my y's, my X arrays and my Y arrays. So there, I need to make some changes to this function in order to actually get the transpose of x instead of x. So it's as simple. Whenever you go, like over here, I'm actually returning the value of x, and all I need to do is make one change. I need to give it a function which transposes this value. Yeah, that's all I need to do. So what I did was that I used this function known as permute, and you can look it up, torch permute, and you can see that torch.permute rearranges the original tensor according to the desired ordering of the dimensions, right? So now, how did I actually pass in the values of this permute function? What I did is simply that I know that by default the dimensions are numbered 0, 1, 2, 3, right? So in this case 0 and 1. And what I need to do is that I need to reverse them now. So all I did is that I passed in 1 comma 0 as my inputs. And now I know that PyTorch will like do a transpose. That is how. And you can actually do it in any order you want. Like, so suppose for example, if you have 5 dimensions, 0, 1, 2, 3, 4, 5, it's 0, 1, 2, 3, 4. You can do 4 comma 2 comma 0 comma 1, and so it will transpose the dimensions in that order, in whatever dimensions you want. So this is how I solve that error. So now I know that.
Understood.
Yeah, is that clear?
Yeah, understood. Thank you.
And when I actually changed that, I actually got a result now. That actually good result now. Anyways, so let's move ahead. Sorry. All right, so that's done now. Now what I need to do is that now I've defined my function, my model, and now I need to define a loss function, right? And the loss function is there is actually in a lot of maths textbook you're going to see a very complex function which is called a logistic loss function, and it contains some log values as well. Like, I mean, I can show you a logistic loss function, and it looks something like this. It contains some log values, minus y times log of h plus 1 minus y times log of something. I'm actually not going to do that. I'm actually going to show an alternative way which works equally well. Log is actually, I mean, I'll tell you why people actually used log. Log was actually used because people actually found it fancy. So mathematicians are crazy. I mean, mathematicians have to do something, right, when they do the research. So they just tend to just put in very complex stuff. You don't actually need this log function. You can just simply scrap it. We are computer scientists, so we are gonna find a hack around it which is gonna avoid all this complex stuff like log and whatnot. So let me just type in, we're gonna do the loss function over here. So here's the thing. Here's how I want to define my loss. My y, which is my actual ground labels, are 1 or 0, right? And whenever my label is 1, I want my model to give me a value as close to 1. And whenever it is 0, I want my model to give a value as close to 0, right? That is how I define my sigmoid function, right? That is how I define my model. So this is a sigmoid function. And so one of the reasons why we use sigmoid function is because it always lies between 0 and 1. And so you want your predictions between 0 and 1, right? It's either 0 or 1. And one reason why we actually use a function and not simply a binary case, like if something predicts 0, if something predict 1, is because we want a continuous function. We want a model to be continuous in the feature space. And the reason we actually do that is because like gradients can only be calculated if your function is smooth. If you remember, when we calculate the loss function, we calculate the gradients, and the gradients can only be calculated if the function is smooth. So what computer scientists did was that they used this sigmoid function which always lies between 0 and 1. And then there's this threshold of 0.5, and whenever the output of the model is greater than 0.5, you can tell that the model predicts that it's a 1. Whenever it's less than 0.5, you tell that the model predicts that as 0. Uh, so I want, whenever my model is 1, the ground truth is 1, I want my model to predict my value as close to 1. Whenever it's 0, I want my model to predict the value as close to 0, right? So loss is basically a penalty if you think about it. Like if you think loss is basically a value that should be minimized. So I will basically condition my loss in such a way that it will give you a greater value in a case that we don't want. So if, for example, the ground truth is one, and my model predicts that the value of the model prediction is less than zero point 0.5, or is or is yeah, less than zero point 0.5, I will basically give it a greater penalty. But if it's greater than zero point 0.5, I will give it a less penalty, right? So here's how I'm gonna condition my loss. This is, by the way, binary classification rules. So I'm gonna define a function, and it's gonna take two things. It's gonna take the predictions of the model, so y prediction, and it's gonna take the y ground truth also. So y, I'll just name it targets, because this is the target, right? This is the target that you want to achieve. And now, the first thing that I want to do is that I want to make sure that these two things are actually of the same length, right? Because how do you calculate? So corresponding to each y, you're gonna have a prediction, but sometimes because of some matrix multiplication error, you're gonna have some error, and these two are not going to be of the same shape, and it's going to give me a problem later on. So I'm just going to make sure that these two are of the same shape or same length. For that, I'm just going to go and use this function or this keyword known as assert, which will basically not do anything if the function is true, but it will give you an error if if the condition is not met. So yeah, that's pretty convenient for us, because the model will simply stop at that point if there is an error at this point. Right. So this is just a, what do you call, bookkeeping step. Nothing of significance. And now what I'm going to do is I need to return some value, and here is what I'm going to do. Just copy me for 1 second, and I'll explain what I'm doing. So I'm doing torch.where, right? Target. So by the way, torch.where. Let's check what torch.where is. So torch.where is will basically return a tensor of elements selected from either x or y. So if condition is met, it will return x. If condition is not met, it will return y for each corresponding element in the data. So basically, there are 147 total elements, 147 corresponding rows, and if I pass it x and y, so it will first check for one row if this condition is met, it will give x if it is met, y if it's not met. For the second row, it will check it again, x if yes, y if no. So that's how it works. So first I need to pass in a condition, and my condition is basically I'll need to check if my target variables, which is this, which is this is either is 1 or 0, because based on that I'm going to be doing some conditioning, right? As I said, so target. So my condition is if is target is equal to 1, right? Now x and y. So what I'm going to do is that I'm going to do 1 minus spread, 1 minus y pred, and y pred, and I'll tell you what that means. Uh, uh, and one more thing. This is because torch.where applies a condition on each individual row. The final resulting element, resulting array, will also be of the shape 147, or how many ever rows there are. But loss is actually one single function, and even in the regression case, we actually did we did a mean across all the loss of all the data points. So that is actually an important step, and we do that over here as well. So that is what I mean by mean. Let's actually check if this works. And I'm going to pass in my target as spread. and my target label as Y badge. Let's see if that works. Yep, you get a loss value which is this. And now and our target is actually to minimize this. And I'll explain what this loss essentially means. So what was my prediction? My prediction was some value between 0 and 1 because that's what our sigmoid function gives, right? So 0.63, 0.65, 0.9014, etc. etc. So corresponding to that, here are the ground labels 110, 111, blah blah. And so whenever my label is 1, I want my model to give me a value which is as close to 1, right? That is the ultimate goal of the model. Ideally, I want my model to predict 1.0, right? But I need to penalize it in some way that it pushes the model to actually go even farther beyond this value 0.63, right? So now if I do 1 minus prediction, okay, but this is not as bad as let's say a 0.36 or a point. If the prediction was 0.1 over here, that would have been really bad. So the model is not doing extremely bad over here, but I still need to push it slightly further. Is anyone trying to say anything?
I was asking, should we take the square of the loss?
No, you'll see that we don't need that. By the way, the square of the loss, the only purpose of the square of the loss was to make the values positive, if you remember, right? But a sigmoid function is always positive anyways. So you don't actually need a square.
But it would also make the relatively bigger values more big and relatively smaller values even more small after squaring them.
No, there are no bigger and smaller values. All values lie between 0 and 1.
Okay.
Yeah. Uh, so, uh, whenever my target value is 1, right? I want to penalize 0.1 with a 0.1 with a greater penalty and 0.9 with a with a lesser penalty. So a good way to ensure that is 1 minus y prediction. 1 minus prediction. So 1 minus 0.63 will give you something like 0.36. That's okay. But if it was, let's say, zero point 0.1, this prediction was 0.1, it would have given it a penalty of 0.9. So that is exactly what I want. And I want the opposite in the case when the ground prediction is 0. So whenever the ground label is 0, I want to penalize 0.9 with a greater penalty and 0.1 with a lesser penalty. So just put a prediction, the prediction value simply over here. And so if it's 0.1, 0.1 is a lesser penalty, and if it's 0.9, 0.9 is a greater penalty. So that's how I define my loss function. Essentially, that's exactly the same as the this logistic loss that I showed you. It's the same. I mean, I can tell you it's the same, and you can analyze it later in a time. Well, I mean, you can make sure, right? You see these elements, right? Like log of 1 minus. So log lies between. Uh, the value lies between minus infinity to sorry, 0 to infinity, right? What's the log? Sorry, it's negative infinity to plus infinity, anyways. But y can either be so. So these values h, x is nothing but the logistic regression model, and x is the input, and y is the ground truth value. So these values always lie between 0 and 1, and between 0 and 1, the values are always between negative infinity and 0, if you remember. Right? By the way, you don't need to remember this. I'm just telling you for your own sake that I've actually done the same thing. And so whenever the target value is 1, you give it a penalty which is log of that value itself. And whenever it is 0, this term will become 0 and this term will become 1. And so you give it an inverse penalty. So that's exactly what I've done over here. Anyways, this works over here. And okay, let's look at some ideal cases. So you want to minimize the loss function as always. Ideally, a loss would be would be minimal if my predictions were exactly the same as my target value. So whenever there was a one as my ground truth, prediction was also one, and in that case, I would get 1 - 1, and my loss would be 0 at that point. And whenever my target value is 0, I want to get a 0 as my answer, and I would get 0 as the answer. And the mean of all zeros is 0. Loss would be 0, and that is exactly my end goal. So my target is to minimize this value. So I've done this now, and now essentially all I need to do is pretty much the same that we did before. That gradient descent algorithm. I'm going to run it for some number of epochs, range 100, for example. Train. So I defined this function over here, train epoch. Epoch basically means one iteration. Epoch is basically an iteration. So what does it take? It takes a model. So logistic regression model. What else does it take? It takes learning rate. What did I pass on last time? I'm gonna say 0.1. 0.1 is a very standard learning rate, by the way. And in Python, by the way, you can represent it as 1e-1, 1e-1. So this is essentially the same as 10 to the power -1. So don't let this e, the e does not mean exponential, it means 10 to the power something. And this is the multiplicative factor, and this is the power factor. So this is a very standard Python stuff. So 1e-1, that means 0.1. And what else does it take? It takes parameters. So what are my parameters? I think it's params itself. Yeah, params. These are my parameters. And let's see. Let me just print the validation loss. So I define this function validate epoch. Which will basically pass in the accuracy. So which will basically right. I think we left it at this point, but we need to actually do something. So I need to define this accuracy over here. So one thing that you need to understand that accuracy is not the same as my loss. So I've taken care of my loss over here, but I want to define my accuracy as well. I need to find out that where does exactly my model find out what my model actually thinks of my data. Does it actually accurately predict a data point as 1 and another data point as 0? So that is not the same loss. A loss is a continuous value. Like, see, this 0.55 that I predict over here does not actually tell you that 55% of the times your model is correct. Right? It is only a numerical metric that tells you how far away you are from your optimal point. It does not represent accuracy. You should keep note of that, right? And I'll explain why this is later on when we go into depth, but I just want to complete this at this point. And I need to define my accuracy over here, which basically takes in my prediction and y. And all this does is that your predictions are basically between 0 and 1. And I'll basically put a threshold over here. Return threads greater than equal to 0.5. So it will first give me wherever it is greater than or equal to 0.5, it will replace it with a 1. If it's not greater than 0.5, it will replace it with a 0. And I need to compare it with my actual y's. And it will basically say that if my prediction, this value is also 1, and this value is also 1, it will give you a 1. And if these two values are not equal, it will give you a 0. And then basically, if I do a mean of that, it will give me a percentage of how many times it was actually correct, how many ones there are, if you think about it, right? Uh, One more thing, I'll actually just convert it into a float. Just it's a standard practice of whenever you do mean, make sure that your values are floats, right? So I mean, I think it applies to here as well. Dot float. Right, right. Alright, so uh, one more thing before that. Just give me a second. Right. Where is my train epoch function, by the way? Right. Here is my train epoch function. It uses something that is a calc grad, and it uses something known as a loss function. So I need to define my loss function, by the way. My loss fn. So by the way, before I do all of this, loss fn is equal to binary classification loss. Uh, so validate epoch. What does validate epoch take? Let's see. I think validate epoch takes the model itself. So I'm going to go through the logistic regression model. And yeah, let's fit that. Let's start. Okay. I'll just name this something else. I think that's creating a problem. And this is yeah. Do you see the problem? So I named accuracy, which is a function, and I also named it a variable. So Python actually thought that I'm referring to the variable rather than the function.
The screen just froze. Like it's not moving.
Or what can you see right now?
You can see the cell 38. A cell after cell 38. You've put your cursor around regression model.
Uh, uh, Wait just a second. Is it fine now?
Yeah. There's some error being shown.
Yeah, exactly. So I was getting an error, and it showed me this free variable accuracy reference before assignment. And I went back to my function where I actually, in this validate epoch, and oh, and here is, yeah, I think it should work now. So I actually used one of the variables named to accuracy underscore rather than accuracy itself. Because when I actually just wrote accuracy over here, my model actually thought that I'm referring to the variable rather than the function. So just some simple stuff. Right. Great. Yep, look at this. So I started with the accuracy of 20%. It kind of became worse at one point, but then started increasing 23%, 50%, 58%, 66%, 70%. And at the end, I'm at 72.73% accuracy. So that is my accuracy for this model using this logistic regression model. Right?
Could you again show like what did you change for rectifying that error?
Yep, sure. Uh, are you getting that error, by the way?
Yes.
Okay, so basically, I went to this function. So I was getting this error at this function, validate epoch, and it gave me an error that is that a variable was referenced before access before assigning a value. So basically, it was basically thinking that this accuracy, which I'm actually using to define accuracy itself, that's not actually allowed, you see, because like I've not defined accuracy over there. So when two variables are of the same name, Python actually thinks that I'm referring to the same variable. So it couldn't identify that I'm actually referring to the function over here. So all I did was that I changed, so I didn't change the name of the function, I only changed the name of the variable to accuracy underscore. And over here as well. I think that should solve the error.
Okay.
And you,
Okay.
yeah, and you always have the link to the notebook. So that's that. If I reinitialize my parameters, let's say, over here, when I run this, I might see some kind of some difference, maybe some variation, some values. But anyways, these are the values. So I have a final accuracy of 73%. That's that. That's perfectly okay. So we've basically completed the logistic regression model. Yeah. And uh, there's one more thing that I. Yeah. Anyways, so here it is. Anyways, uh, this is a lot of code, but I actually want to refactor this because this is a lot. This is very clunky. I mean, it's. I mean, it just distributed all over the place. I probably want to like just make it more concise, and I want to like put it into like proper classes and whatnot. So I'll just spend some time doing that. I think it's a very good exercise, and it's going to become really handy when things become really complex. So my model. So what are the components of my model? Let's just enumerate them. Here is your data loaders, which contain your data sets, everything. Data loaders is one component, which is a class in itself. You have your model, which is nothing but that mathematical function which takes in an x, gives you a y. You have optimizer. Right? And yeah, these are essentially the things that you need. Right? And some other, what do you call, functionality like validate epochs and stuff like that. And I'll put them into one single big class, right? And I'll name this something. I'll just name this deep 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 learner. I'm going to define a class known as deep learner. Right? Uh, okay, so by the way, first before that, let's actually just make everything very streamlined. So first, coming to data loaders. So I'm actually gonna just do what I did before. PyTorch actually gives me data loaders themselves. So from torch.utils data import data loaders, data loader. Yeah.
So, very sorry to interrupt, but your screen is again frozen. Now it's
Yeah,
refreshed.
I'm actually very sorry. I'm actually working on my data. I don't have Wi-Fi today. As I told you, I'm actually traveling this week.
Okay.
So very sorry about that, but I'll
No
try my
issues.
best.
Just yeah, the code is getting transmitted to us with a bit of lag. So.
Yeah. I think that helps. Thanks. Yes. So I'm just streamlining everything. So my train, it contains of my train data set, and you need to make sure that your data set exists before. And some batch size of 16 works well. I think Prabhava asked at one point that uh, should the batch size always be a multiple of two? So that's a good point. Not exactly. Ideally, your batch size should be a power of two. Like 2, 4, 1, 2, 4, 8, 16, 32, 64, 1, 5, 1, 2, 4, 2, 2048. So the reason that is because you see that all codes, all memory functions are binary, right? It's either 0 or 1 when it goes to a compiler. And so when you, so all your memory functions itself are allocated in powers of 2. So you get allocated, and that's because of constraints on array allocations. I mean, like if you do, if an array has to be allocated in one dimension, the same size has to be allocated in another dimension. So at that point, you're just doing the square. And if you allocate it in a third dimension, you'll have 2 to the power of 3, or anything times 2 to the power of 3. Yeah. Fourth dimension, 2 to the power of 4. Yeah. That is actually the reason it's actually 4. You can, ideally, no one's actually stopping you to actually assign it a value of 15. It's not going to give you an error. But it's actually just wastage of memory, because for this to be allocated, your memory will have to allocate anyways a memory size of 16, or 2 to the power of 4. So why waste that one extra memory bit? Just assign it 16. So that's the answer. And for any one of you who are electrical engineering student and you have come to your second year, in second year you had that core called microprocessors. You actually learned about this memory allocations. And similar to that, you have data loaders, data loader test, bset, batch size. And as a rule of thumb, your testing batch size should always be double the size of your training data set. Why? Because training data set, your training data loaders actually need to keep track of two things, if you think about it. The actual value of the array, and also the gradient values. Because you've defined that you want to calculate gradients, and you're not actually manually calculating gradients. So PyTorch needs to keep track of those gradient values. So you see, like in testing you actually don't need gradients at all, so you're actually saving that extra 50% amount of space. So you can simply like double your batch size and it will basically be the same. This works, I hope. Yep. Next comes your model. Your model is nothing but I'm actually not going to define a function. I'm actually, everything should be classes, by the way. So class, logistic, regression model. It's not going to inherit from anything. Oh, sorry, it is going to inherit from something. All deep learning models, right, should be inherited from one particular class, which is known as torch.mn.model. I'll tell you what, it actually gives you some very good functionality when it comes to neural network things. Automatic, you don't actually have to define parameters outside of your model. It will automatically like define parameters. It will register each individual component as parameters, as modules. So what you can do is you don't actually need to, like when your models actually become very big, yeah, you don't actually have to go through each line of code, like what's doing what. It will basically divide into modules. You can access them separately. So that's what torch.module, nn.module does. It also has very good uh, so it has CUDA capabilities, meaning you can actually transfer it. It has code that is corresponding to you transferring the model to your GPU. And we'll look at that later, not in this class, but maybe next class. So there's an init, blunder init, as always. So this is a function that is about initializing of the class. You need to pass in like how many features you want. So in our previous case, that was 5. So W1, W2, W3, W4, W5. So that can actually vary, like depending on your class. So I'm gonna Just put it as a variable. Uh, you can choose or not choose to put a bias, so I'm going to do that as well.
Had a doubt.
Yeah, sure.
Um, every time like we initially randomly give values to the weights and the bias, and then we go along the gradient to update them so that
Yeah.
we get the correct or the desired value of weights. So if we run the experiment again and again, we would get different trained weights at the end, or they should be similar.
No, they can be different. So, by the way, and it doesn't matter actually. See, you don't actually care about like what exactly the value of your training weights are, right? You only care about like how the model is performing. So, just to actually tell you as a fact, let's see what the value of params are. Params are 0.4892, 0.6912, 0.10894. Now you tell me that let's say in another scenario, if I reinitialize it at something else and I get the final value as 0.4893 or 0.449, for example, right? That shouldn't necessarily change the output of the model, right? Like it can change the loss value by some value, but it won't necessarily change the accuracy of the model, right? Because where is my accuracy code? Yeah, so this is my accuracy over here. So it may be possible that even by slight variation in this W1, this Y value doesn't change by so much that this prediction is completely changed out of the blue. Yeah. So yes, they can change, but we don't care about that. So uh, whenever I think we talked about this, whenever you're actually inheriting. So first, before actually inheriting, before actually initializing this class's init function, you first also need to do initialize the parent class. This is torch.nn.module. Why? Because it contains some really good functionality that we want. So I need to do that. I'm going to do that. So uh, so um, yeah, this is done. So super.dunder in it. Then one all you need to do is that my model actually contains some weights. I need to do that. So I'm not actually gonna define it like randomly by myself. I'm actually gonna let PyTorch do that. So why should we actually write code once we've already defined it, right? So I'm just gonna do torch.nn.linear. Actually, I'm just bored of typing dot torch.nn again and again. So I'm just gonna do import from torch.nn. Please do that with me. From torch import nn. I'm gonna do that, and so now I'm not actually gonna need this. This. Okay. So nn.linear. So everything related to neural networks or like deep learning is present in this torch.nn. NN stands for neural networks, by the way. So nn.linear is actually the same as your. So basically a function which contains weights and bias, and you can pass in a value. It will basically do matrix multiplication and give it to you. So here is it. Applies a linear transformation to the incoming data. Y is equal to x a transpose. So a is the weights, for example. B is the bias, and so x matrix multiplied with a, which is the weight, plus bias. So nn.linear basically handles all of that stuff for you. Right? And you can actually make sure that B can be a parameter or not be a parameter. So bias may or may not be a parameter depending on the use case. And why I actually chose to take bias as a parameter is because I'm actually going to pass it over here. So it's going to take n in as one of the inputs, and then out features. Out features is basically going to be we have one output, if you think about it, that is a value between 0 and 1. And bias is equal to bias depending on whatever that input is given as input. That's it. Right? now I need to define something that that handles like what happens when I actually pass in a value to this. I actually want my logistic regression model to actually also act as a function, so I can actually pass in x as an input to it, and it will give me a y, just like before, because it's very convenient, right, to actually have your model act as a function itself. Yeah. So for that, I'm actually define a function known as forward, which basically means forward pass, meaning I given an x and it does whatever matrix multiplication, it goes forward in the loop and gives me an answer. Now, why exactly I've defined it as forward over here? I'll tell you why. Just give me a second, but just copy whatever I'm doing over here for 1 second, and it's gonna take in one input x, which is gonna be a batch of data, and I'm just gonna do a torch dot return torch dot sigmoid self dot weights, which is nothing but nn dot linear, which does nothing but that what we call, which does nothing but basically does that matrix multiplication for me. So I'm not going to do that matrix multiplication by hand. So self dot weights acts as a function now, and it's the case for this also, by the way. nn dot linear is actually a class, but it actually acts as a function. You can use it as a function, and this is actually because of this forward class over here, and I'll tell you why. So that's that. So I've defined my forward function. Backward and all, actually, nn dot module can handle all that backward and stuff. Yep. So yeah, that's my model. Actually, see if this works. So model, I'm going to initialize my model. Model is equal to logistic regression model. It's going to take in nn5 and out 1, and bias is true, so I'm just going to leave it as is. And I'm just going to do model x batch. Let's see dot shape. I hope it works. Yep, it works. And now here's something very interesting. Here was a function. Here was a class, and I just passed a value to the class as a function. Like I treated this class as a function, and it still gave me an answer. And I didn't actually do anything specific over here to actually do that. So how did it actually do that? So let's actually define that. Yep. So whenever you want to use a class as a function, right? So it's actually defined in this another dunder thing known as dunder call. Right? Yeah. And so whenever you define this, right? And I'm actually not going to do that. Whenever you actually define this, you can actually use a function, a class as a function. So I'll just show you an example, just a very basic example. Class, I don't know, random, temporary, nothing. There's going to be some init function, right? And I'm not going to do anything with it. But then I'm going to do a dunder call and self x, and I'm just going to do return twice, return 2 times x plus 3, for example. Let me just actually define this. Now let me actually use this as a function now. Yep. So I actually used a class as a function now. So I did 2 times 2 plus 3, and it gave me a 7. Right? So I'm just going to delete this. I don't need this. So that is it. That is how you actually use classes as functions themselves, and that comes very handy in neural networks because it's very hard to handle models otherwise. But I've not defined a dunder call over here. So how did my model actually know that? So the magic actually comes from this nn.module, which actually already has a dunder call defined in it. So let's actually see the source code of nn.module. to see the source code in Jupyter Notebooks, all you need to do is a double question mark followed by whatever function you want to see the source code of, and it's going to give you a source code. Let's see dunder call, dunder call, dunder call. Call, call. Yep. So there is something known as call implementation, which is actually also used by. Oh, here is dunder call. Yeah. So call is actually replaced by call IMPL, and the definition of call IMPL is, look at this. Uh, it goes to my function and it basically uh, goes to the forward function. So yep. So it goes to the forward call, something known as forward call, which is nothing but self dot underscore slow forward, and essentially, if something is set which we've not set, else just go to self dot forward. Yeah. So forward call is nothing but a call to this function that I'm going to define, which is known as def forward. So whenever you use nn dot forward, whenever you use nn dot module, all you need to do is to define a dunder call, is to define a function which is def forward. Okay? And it's going to take in an x and it's going to do something and it's going to return a y. So that's that.
Always when we're using nn.module, do we have to follow this scheme of first giving it uh, that thing, that forward function?
Yes, in most cases, yes. I mean, you can obviously define it as per your own choices, but like this is the default that nn dot module will give you.
Okay, so going from here, like we should try to do this as a thing,
As a
like
thing,
where.
yes. Yeah. It's a very good practice, actually. I'll tell you what. See, look at how we actually wrote our code over here. We defined a function over here in which weights were defined outside of the or outside of the model, which ideally you should not have to do. You should not have to handle these two things separately because they're part of the same. And then I have to actually define these things separately over here, and I mean it's very clunky. You see, it's spread all over the place. I'm actually just trying to condense it all into one place. So in order to associate weights and biases as part of your model itself, you need to make your model a class. You understand that? Because definitions by themselves cannot store values, cannot store weights and biases. Classes can store weights and biases. Yeah. So I've taken care of that functionality, and now I also want the functionality of my class being a function in itself. Right? It should take in an x and it should give me a y. Yeah, and that I've taken care of using this formula, and this is how PyTorch gives you this ability. Yeah. Yeah. So that is how you should actually do going forward. And by the way, once we've defined this def forward, you're not going to see def forward anytime else. So now you only see, now I'm only going to do logistic regression model. I'm going to treat it as a function and it's going to work flawlessly. All right. So next thing is, okay. So by the way, I don't actually also have to define my parameters separately. nn.module takes care of, it actually registers all the parameters everywhere throughout the model in something known as dot parameters. So if I go over here, you're going to see that parameters, the parameters are already been defined, even though I did explicitly define parameters. But what nn.module did was that it detected that there's that nn.linear over here. And nn.linear has a property in itself which says that that it has some parameters. So it went to those parameters and it registered those parameters separately. So now I don't actually need to define my parameters separately. So that's one good thing. So these are all the good things about what do you call your model parameters. All right. So next thing is optimizing. optimizer. Let's see what optimizer actually did. Optimizer was a function. Oh, I didn't define my optimizer actually. If you think about it, so I actually had to do all of these things separately. I calculated the gradients. I did the update step. I did the gradient zeroing out. So I should have to do this. All this is the work of a single class known as the optimizer. I'm just gonna define that as optimizer. So what exactly do I need for this? By the way, I don't need nn dot module over here because uh, there is no functionality of nn dot module that you need over here because it does not have parameters on it of its own. It does not have. You don't actually need gradients. So optimizers takes care of other gradients, but it does not have gradients on its own. So you don't need nn dot module as such. Uh, Again, as such, there is a def in it. Self. You need some parameters, right? Because it handles the parameters of something, which is the model. And you need some learning rate, to which I'm going to give some random value, default value. Uh, in the initialization, I'm just gonna store these values as my model, as my class attributes. All right. So next thing. So there are two things that I need to take care of. Is one thing that one thing is the update step, which is this, and the second thing is this. I need to zero out all my gradients after each step. The reason I need to do this is because by default PyTorch keeps on adding the gradients. So you don't actually want that. You just want to clear out the gradients. Um, so the parameter update step, I'm going to define as this. Uh, F step. And all I'm going to do is that, just copy me for a second, with torch.nograd for p in self.params, p minus is equal to self.lr times p.grad. Okay, so here's what I'm doing over here. So the first thing is torch.nograd. Why did I tell torch to not consider the gradients? Well, that's because PyTorch by default keep tracks of all the operations you've done with your tensors, with your parameters. So that is how it keeps track of like what gradient, how to calculate gradients. You see, because like let's say you have a function like w1 times w2, okay, sorry, f1 times f2 times x. How do you calculate the gradients with respect to that? First, you calculate the gradient of x with respect to f2, and then you calculate the gradients with respect to f1, and then you do a chain multiplication. Do you remember this? This is just high school stuff. So this is called back propagation. And so how PyTorch keeps track of this is that it's going to keep track that I first pass it through a function which is f2, then I pass it through f1, and so it's going to keep track that because this was the order of the steps that you took. This is how you calculate the gradients. But here also you're doing some operation, right? P minus is equal to self.lr times p.grad. This is not meant to be, calculated gradients with respect to. Yeah, you only want to calculate the gradients with respect to the model layers, right? And so in order to tell the PyTorch to actually ignore this step in its computational graph, in its computational memory, you're going to tell PyTorch that just for this step, just ignore the gradients, right? So PyTorch is not going to keep track of any gradients at this step. And this is just the standard thing that we did, that just go through all the parameters and subtract the gradient times the learning rate. This standard. And finally, def, that is zeroing out. So I'm just going to name it zero grad for p in self.plans, p.grad.data, because I need to change the data of my gradients as zero. Uh, and I'm going to replace it. I'm going to use a PyTorch function to replace it with a zero. So whenever there is, so dot zero is actually a function. So torch dot zero, for example, zero underscore, by the way, torch dot zero and torch dot zero underscore are two different things. And whenever there is a underscore, right, just know that that underscore basically means that you're replacing something with another value. You're not making a copy, you're replacing it directly. Uh, Fill self.tensor with zeros. That is what torch something dot zero does. So that is my optimizer. Yeah. Let me just define my optimizer. Optim is equal to optimizer uh, model dot. So my parameters are model dot parameters. Learning rate. Learning rate. I'm gonna let it be as is. Let's see if optim actually exists. If it's not, yep, there is no error over here. That's good. Uh, Optimizer is
Could
done.
you
Oh, one thing
explain the
else. Sorry,
optimizer
I
part
need to send
again?
it. Is anyone saying something?
I was saying, could you explain the optimizer part again?
Could I do what? What do you want to know?
I was saying, could you explain the optimizer part
Just a
again?
second. Just a second. Uh, I can't hear you. Hello.
Hello, am I audible?
Yeah. Tell me.
Yeah, I was saying, could you explain the optimizer part again from
All right. Sure.
torch.nograd?
All right. All right. Okay. So, can you guys tell me if you've learned about how to take gradients of a function in your lecture classes? Or do you have an idea like why you actually take how you actually need to take gradients in order to minimize the loss function? Do you guys understand that?
Yes,
Everyone, there's a question for everyone.
yes.
All right. So if you notice that we didn't actually calculate gradients at all, right? Throughout the entire model, right? We actually just let PyTorch keep track. We let PyTorch keep track of all these things by itself. And how does it actually do that? Let's actually look at it. Um, Let me just actually go and just let's look at what model is essentially. So let's yeah, here's what it does is first you take an x, you multiply it with w, you add bias, you pass it through the loss function, right? And in the loss function itself there's this torch dot where, and then you take a mean. Yeah. So when you get the output of it, the PyTorch actually keeps track of what function was what operation was done on the tensor last. So over here, it first keeps track that for at the very end there was a mean taken. So corresponding to that mean, it's gonna take a gradient. It's gonna calculate the gradients. Yeah, because like when you take the mean, what's the gradient of x with respect to a value which is the mean of x? Yeah, it's gonna do that. The value that you're going to get is also going to have a grad function which is going to correspond to this torch dot pair. Yeah, so you're going backwards. So this is called backward propagation, by the way. Yeah, so if you remember that values are calculated inside out, but gradients are calculated outside in a function. This is just high school mathematics. So that is how PyTorch keeps track of it. But now there's another operation that I'm doing over here, which is p minus is equal to learning rate times gradients, right? This is an operation that PyTorch is gonna consider that as a valid operation. And so the next time when I'm gonna calculate the gradients, it's gonna calculate the gradients with respect to this step also as well. So do you understand that there's a problem in this case, Prabhav?
Mm, yeah.
If you don't, I can explain. Okay, no, okay, and I think you don't. Well, so this is not part of my model if you think about it. Okay. Let's just look at a logistic regression. So This is, by the way, the definition of the sigmoid function: 1 times 1 plus e to the power minus something. So gradients are supposed to be calculated with respect to your model, with respect to the operations of the model. So how gradients are calculated is you take an x is multiplied with some weights, it goes to some loss function. So the gradients are now calculated. First you take the loss with respect to the loss function, then you take the loss with respect to the weights, and then with respect to the inputs themselves, and that is your output gradients. That is the gradients with respect to which we need to update your parameters. Do you understand that?
Yes.
Now, this operation that I'm doing over here is meant to update your parameters, but this is not part of your model as such, right? This I'm doing this outside of my model. Yeah. So I shouldn't have to calculate gradients with respect to this step. That's not a valid step. That's because this is not part of my model. This is like completely separate from my model. Do you understand that?
Right.
Are you sure?
Yes.
Okay. Now, so but PyTorch doesn't know that this is not part of your model, and it's gonna keep track of this step as well. Okay. So I just need to tell PyTorch that just for this particular step, just please don't keep track of this operation. Because what's gonna happen is that next time, see, in one epoch it's gonna work probably okay, but the next time I'm gonna calculate my gradients, it's gonna calculate my gradients with respect to this step as well, and that is not valid.
Right.
Yeah. So I need to tell PyTorch that just for this step, just ignore the gradients, ignore the gradient tracking for this particular step only. So that is what torch.nograd does. It tells PyTorch that don't take gradients for this step.
But we'll do this for every new epoch, right?
Yes. Yeah, but like it's gonna, but PyTorch actually keeps track of all the operations like since the beginning of time.
Okay.
Actually, this is also a reason why we do zero over here, right? But what happens that zero is done at the end, right? So what happens like before this? Before that, PyTorch is actually gonna keep track of this, and it's gonna take the gradient with respect to this as well, and that is not valid. So I need to tell PyTorch that this is not part of my model, and I need to exclude this from the tracking of gradients. So that is what torch.nograd does, and it's only for this particular step, no other step.
Okay.
Uh, that is done. Optimizer is done. Now I need to define my loss function. So loss is also a class. Everything is a loss, by the way. But for now, I'm actually not going to define it on my own. I'm just going to use what is defined by PyTorch. But for now, let's actually just leave it as is. I'm just gonna copy this loss function in here. Primary loss function. Right. Loss function is fine. Now I need to define my final deep learning class, deep learner, right? And let's just do a class init, definite, self. Gonna take in some training data loader, some validation data loader. It's gonna take in a model. It's gonna take an optimizer. It's gonna take a loss function. Anything else? Yeah, I think that's done. Yeah, that's all. So data loaders, it took data loaders, it took model, it took optimizer, it took mouse. So and so basically, this deep learner is nothing that one class which is home to all these other classes, because I shouldn't have to handle 4 or 5 different classes, right? I should be able to handle just one class. So that's exactly what I'm doing. So just self dot ndl is equal to ndl self dot validl dl self model is equal to model self dot optimizer is equal to optimizer and self dot loss sorry, optimizer is going to be a function. So I should only have to pass in the function and not the initialization itself. So I'm going to initialize it on the spot. Model dot parameters, and maybe I can pass in. Uh, Maybe I can pass in. By the way, not model dot parameters, self dot parameters. And learning rate. Learning rate I'm going to leave as for now. All right. So that is it in initialization. What else do I need to do? I need to calculate the gradients. So here I need to first, I'm going to get an x. It's going to pass it through the model. It's going to get some loss and it's going to do, it's going to calculate the gradients using loss dot backward. So, oh, by the way, nn dot modules have a dot forward as we defined that refers to the forward pass, and nn dot module internally also have a dot backward defined which refers to the backward pass, which is nothing but calculation of gradients. So I'm just going to calculate this. I'm just going to copy this over here. If calculate, but it's going to have self and x, y, and model. I don't need because I've already stored them. Uh, Sorry, it's going to have. It's going to take a batch of data. It's going to also take a batch of y's. As such. So this is this. Loss dot backward. By the way, it's loss dot fn is not defined, so I need to do self dot loss fn. Oh, and this is also self dot. All right. So I've defined my calculation of gradients, and I'm just gonna define that train epoch function as well. Where is it? Yep, def train epoch. Uh, but I don't need to do all of this at once. Okay, let me just self. I don't need model because I already have self dot model. I don't need params because I have model dot parameters. Learning rate, I may want to. Okay, I don't need learning rate as well because optimizer actually already has a learning rate because I've already defined learning rate within the optimizer. Uh, so what I'm going to do is for X batch or Y batch in train DL, I need to do a self dot calculate gradients. It's going to take X batch, Y batch, and it's not going to take the model. And after that, all I need to do is self dot opt dot step and then self dot opt dot zero. That is my train epoch. All right. Next is all those standard stuff. Yep.
Self.opt was the back propagation part, right?
No, self.optimizer. The only function of self.optimizer is to the gradients were already defined by the way. Okay, let me tell you what happens. So so when you do you calculate a loss at this point, and then you do loss dot backward. Basically, you calculate the gradients with respect to your loss of everything of your parameters with respect of your loss with respect to your parameters. And so what it does is that it's going to define with every tensor, right? So for example, parameters itself are tensors, weights and biases are tensors in themselves. When you do dot backward, it's going to assign another attribute to that tensor, which is dot grad, right? So let me just show you. Yep. So this is the value, right? And this is stored in params.data. Okay, so params.data is nothing but, sorry. for P and parameter data print P. Let me just do that for you. Yeah, I think I've deleted that, but anyways. Uh, so every tensor has two parts, which one is the data and one is the gradient of it. Yeah, which is why I actually stored only half the size of my testing data set over here, because like if there are 16 data points worth of data, there is also 16 data points worth of gradient values. And so what the what the optimizer does is that it simply taps the gradient values, which is stored in this dot grad attribute. So there is that p dot data, which is gonna give you the actual value of the parameters, and there is that p dot grad, which is gonna give you the gradient values. And dot backward simply calculates those dot grad values. The only job of the optimizer is to take those grad values and to do that parameter update step. It doesn't calculate the gradients. Is that clear?
Yes.
You can actually change the functionality. Look, I mean, no one's stopping you if you actually calculate the gradients from the optimizer class, right? But I'm just trying to demarcate things very clearly, because the job of the optimizer is not to calculate the gradients. The job of an optimizer is to take those gradients and directly do those updates. So I'm just trying to clearly demarcate what each class is doing. But as an exercise, what you can do is you can simply you can go ahead and do whatever you want, change the functionality. And then the standard stuff, let me just go. Accuracy and validate epoch, I'll need this, I guess. So I'll just copy this. Um, this is fine. I don't mean why. Oh, sorry. Let this be as is, but it's going to go self, comma, threads, comma, y. And it's going to give me this value. That's fine. Then you have def validate epoch, accuracy is equal to blah, 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 in self dot validate. And yep. And one final function that I need to define is that one function that's gonna take care of all of this. That's gonna take care of one single iteration. So I'm gonna name it as fit uh, self and epochs, number of epochs or number of iterations that you want to run it as by default one. Uh, for epoch in epochs in range epochs. Self dot train epoch that, and then I'm gonna do print um, epoch. I'm gonna use something known as an F string, which is a which is a very advanced version of a string in Python, in which you can actually, and I'll tell you why. You can do like value formatting in it really well. So whenever I do curly braces, it's gonna actually it's gonna tap in the value of this variable within the string itself. So just a very trivial thing. Just copy me if you want. Um, oops, shouldn't be that. It should be self. This should be self dot model. It should be self dot accuracy. Make sure you don't miss out these things. Uh, yep. Which is this. I hope this works. Let's see if there's no error. There is some error. Oh, I didn't close this. Yep. Oops, that works fine. So I'm just gonna do a PL learner. Okay, let's have it. I'm just gonna name it learner. Learner is equal to DL deep learner train DL valid DL. What was the name of the model? I think it's test DL, but anyway, it doesn't matter. Uh, I've defined my model as well. I've defined my optimizer as well. And I've defined my loss function as well. Hope it works. If it works. And I can do learner.fit and it's gonna give me some values. Oh, sorry, self.optimizer and not self.opt. Okay, method object is not iterable. Okay. Okay, so there's some problem with the optimizer class. Method object. Oh, okay. So when I passed my parameters, it should be you should give the square, I mean the round brackets as well, because by default this is just a function, right? This is just a generator, but this is an object with square brackets. I think this should work. Yep. So at the end of the first epoch, my accuracy is 72% as before. Let me just do 10 epochs maybe, and let's see what we get. Oh, I'm not getting any improvement. And I'll tell you why. So I'll tell you the reason why this is not improving. So a logistic regression model has only one global minima. There is no local minimas. So do you know the concepts of minimas, by the way, everyone?
Yes.
Anyone else?
You see, it only has one global minima, right?
Yes. Only one minima, and that is the global minima. Yeah. So there is only like so the gradient has actually reached like after one epoch it has reached the global minima, and there is no scope to go down any further. Yeah. I mean, you would have seen the accuracy increasing if there was some scope of improvement, but there is no scope of improvement in a logistic regression model. That is the
Okay.
reason. Anyways. So yeah, this is your logistic regression model, and you've completed logistic regression.
Wait. So when we hit that value where we can't really go any better, so should we stop training at that point?
Yeah, I mean, ideally, you should get the result in just one or two epochs. So I mean, one epoch is fine, by the way. 73%. Look, there is some variation, but like you won't be able to go beyond that. Yeah, so only for a logistic regression model, right? Not for other models. So if there are like let's say more number of weights, which we'll see in the coming few minutes, you'll, you'll see that the performance actually increases here. So this is a part of lab one, and let's actually move to lab two sometime. And let's actually do something. And oh
Could you share the lab 2 link?
yes, sure. Wait, wait. Here is link to lab two. Right. So the first thing that I'm going to do is just I'm going to do some standard importing. Um, I'm actually going to be work now. Let's actually move to a newer data set. I'm actually bored of the Titanic data set. I'm actually going to move to the Mnist data set, which is a data set containing of handwritten digits. And your task is to classify different image. So, for example, let me just show you. So this is what the Mnist database looks like. It contains of some 60,000 or 70,000 handwritten digits, which are written by hand. And you need to train a neural network model or any model that can detect which digit does it correspond to. So you're doing handwritten digit recognition, basically. Uh, so let me just download that data set first.
Hand it out.
Yep.
So for example, like when we talk about back propagation or convolutional neural network, should they actually refer to the fundamental papers? Like for the MNIST dataset, should we look at Leakin's paper or something like that, or like the up to date forums and all are fine for that?
Yeah, well, for most of the cases, you don't even need you don't need to read the original paper, unless you're doing some really advanced stuff. Like there is something which is not addressed anywhere else, and so you go to the original paper to see like how the author has addressed that. But like most of the cases, you don't actually need to even go to the forums or anything like that. Like you just need to have some basic idea. For example, I have MNIST or I have convolutional neural networks or logistic regression model for that matter. The amount of information that I give is probably enough to like get you started with like most of your applications. You don't actually need to go and like go into like some really deep stuff and stuff like that. So like just stick to like what you essentially need, the fundamentals basically, and not really like don't try to go like really deep. That's my advice. So PyTorch actually provides some these data sets. We're actually going to be using the Mnist data set, by the way. So PyTorch actually provides the MNIST dataset in another PyTorch submodule known as Torch Vision. So look at this. PyTorch package consists of popular datasets, model architectures, common image transformations for computer vision. So Torch Vision is the computer vision library for PyTorch. And it contains, so MNIST is actually a computer vision dataset, right? So I'm just going to go import, I'm just going to import Torch Vision first of all. I'm also going to need some random stuff like import torch from torch import, and then what else do I need? Let's just leave it up like that. Yeah. So let's look at the Mnist dataset. Torch vision datasets, and look at the right side. You'll find the Mnist dataset. Yep. So here's how you download this dataset. You're gonna have to download the training images and the testing images separately. So here's how you do that. You just do Mnist train images equals vision datasets dot, dot mnist uh, root is equal to, I'm just going to leave it empty. Root is equal to empty means it's going to download it wherever you are in the root directory of your Google Collab. Train basically means that is are you trying to download the training set or the testing data set? So train is equal to true. Uh, we're going to look at transforms in a second, but download is equal to true, by the way. And download is equal to true. Similarly, I'm just going to copy this and I'm just going to do mnist test images, and I'm just going to do train is equal to false. And let's see if that works. So it's actually downloading the dataset, and let's see what exactly we get. So let's just look at this, the length of the images that I have. So I have 60,000 images in the training dataset, and maybe how many? 10,000 images in the testing dataset. So that's good. Let's actually look at like what the dataset actually looks like. So Mnist train images. Let's look at the zeroth index of that. It's a pil.image.image. So pil is actually it's called the Python image library, and it's the standard library to handle images in Python. We're gonna use it a lot of times, by the way. So and it's actually a tuple if you look at it. So it's actually a tuple, which is the zeroth element is actually the image itself, that is the data, that's your x. And on the right, you have the label, the ground label, which is 5. So it must be a handwritten digit of 5, right? So I can also index the zeroth element of this tuple, which is going to give me the image itself. And if you look at it, you actually get what image you have. So this is the image that we'll be working with. All right. Here's one small problem. PyTorch doesn't understand images. It only understands tensors. So you need to convert all of these images into tensors. Yeah. Ideally, what I would have done is that I would have just iterated through all these images and replaced the zeroth element with this corresponding tensor. But if you remember that I have tuples over here and tuples are not mutable, so I cannot do that directly. So for that, Mnist provides me with an API which gives me a function known as transform, which will let me apply any function over each of my data set. Yeah. So there is this transform that is applied to x, and then there is this target transform which is applied on the y's separately. I don't need to apply anything on the y's. I only need to apply it on the x's. So for that, I'm just gonna go transform is equal to uh, I need to convert images to tensor. So let's just see how you do that. PyTorch convert an image to tensor, and let's look at some forums. All right, so it tells me that from torch vision, there's a submodule known as transforms. Oh no, this is not the answer. Uh, all right, here, transforms.to tensor. So is equal to torch vision dot transforms dot to tensor. That's the transformation that I need to apply on my data set, right? And I need to do the same for my what do you call my testing data set as well. And now let's actually look at like what exactly is the zeroth element. Now you see that this is a tensor. Yeah, we're not getting a shape anymore, we're getting a tensor. So this is a tensor of shape 28 by 28, and then this is the batch size of 1. There's one channel, 28 by 28 pixels. So Mnist dataset basically contains of 28 by 28 pixels, um, and that's about that. All right. Uh, all right. Standard stuff. You need to first, you know, create your data loaders. So for that, I'm just going to go from torch.utils.data, import data loader, and then you have traindl is equal to data loader. And to a data loader, I'm actually going to pass the data set itself, which is nothing but mnist train images. Anything else? Batch size 16 is fine. Yes. Same as before, by the way. Nothing different. And I have my testing data set, which is the same. Mnist test images batch size is equal to 32. Let's see if that works. Next, iter. Yep, it works. So this is going to give me x, one x and one y. So the zeroth element is going to be a tensor, and the first element is, and you see over here, I have 16 elements in one batch, and each element is 1 by 28 by 28 in size. And then the first element is going to be nothing but what do you call your y labels, which is 16 labels corresponding to each of the 16 items, 5, 0, 4, 1, blah blah blah. So so it goes from 0 and goes all the way up to 9. So 10 digits. Correct. That's done. Uh, what else do you need? Actually, there's one thing that I want to do, that I want to define a class that also handles both of these things separately. Like I shouldn't have to handle these two things separately. They should all be under one roof. Yeah, because like a model handles them separately. So I'm just gonna do a function known as get DLs. Uh, NDS test DLs batch size is equal to 1 by default. Yeah, I think that's true. That's nice. Oh, sorry. Yes. Yes. So I'm just gonna copy this, by the way. Batch size is equal to VS. Over here, it's going to be batch size times 2. This is going to be NDS. This is going to be test DS. I'm just going to go and do return NDL. Are you guys following me? All right. Uh, okay. Now let's actually come to the most important part, which is the model itself. And what we're going to learn over here is neural networks. Congrats. So this is the big part, I guess. So what we're going to do over here is we're going to look at a very basic neural network, which is known as a multi-layer perceptron. Uh, what have you guys actually learned in your lecture classes? So okay, so you're going to be learning about neural networks. So I guess this is, so you're going to probably learn about it a little bit in advance. But I see that you guys have already learned about training a perceptron, which is nothing but a logistic regression model and a linear regression model. Uh, okay, let's actually look what a neural network is. A neural network is nothing but an extension of the logistic regression model. So the problem with logistic regression model is that the entire complexity of the model has to be fit using only 5 parameters. That is those 5 values of the weights and maybe one bias. So maybe 6 parameters in total. Yeah. And sometimes that's not enough to actually give you the desired complexity or the desired, ability of the model to fit the data. And so you need to increase this by a certain amount. So one way to do that is actually, so for example, y is equal to wx plus b. We saw this, right? What if you pass this to another w, which I'm gonna say w dash. I'm gonna take this y and gonna pass this y as another x to another w, this wb, but pass it over here as another b. And I pass this again as an input to another w, which I'm gonna name as w dash dash plus b. So I'm basically doing multi layers. I'm doing layers over layers of things, and this is what I call as a neural network. Let me just show you. what a neural network looks like. And specifically, I'm looking at a multi-layer. So you must have seen this image sometimes. This was the input, and we did some matrix multiplications over here. I mean, this might look complex, but it's essentially just a matrix multiplication. Oh, okay. I think this is a better representation. So this was some input. You multiplied it with some weights, and you got some state over here. That is some y, right? And you added a bias to that, and you stopped over there. But now you're doing it. You're taking it one step further, and you're again multiplying it with something, and you're again adding a bias, and you can do this for 2 3 4 times. And by now, so now you're actually increasing your model parameters by, let's say, from 6 to 100 maybe, and maybe 100 parameters are enough to to give the desired complexity. That's that. Okay, so let's actually just code it up for a second, and we'll see. Srujan, the lab, I'm trying to wrap it up really quick, but it'll probably go for about half an hour more. So, let's code this up. I have a class module, right? Which gonna take from nn.module as before. Uh, and I'm just gonna do uh, if init self. Anyway, how did we define my module over here? Yep. I've just copied the logistic regression model because that's what I'm extending, and I'm just gonna name it model for now. Or MLP model for multi-layer perceptron. Right? So it takes an NN, it takes an out as well, by the way. Because in that case, I didn't actually need. Uh, in that case, I didn't need an N out because I knew that N out was going to be one itself. But may not be the case over here. We have 10 different outputs, 10 different classes to classify N out. So I need N out, and yeah, bias is equal to 2. Bias is also an option. Uh, and self.weights becomes self.layers because now there are multiple layers. I'm gonna make it a list of different linear weights. So there is nn.linear that takes nn, and the output is, let's say, 50 outputs. Let's say, for example. And for the second part, I'm just gonna do nn.linear, and it's gonna take 50 inputs, which is whatever the output of this was, 50 inputs and 10 outputs, or n out number of outputs. Right. So this is my model diagram. F forward will become now for layer in self.layers. X is equal to layer X, return X. Let's see if this works. Model is equal to MLP model, and N is 28 times 28. So what I'm going to do is that what I'm going to do is that because we have only seen how to handle like one-dimensional data, right? Like, for example, like the second dimension itself is like the data points itself, but like the first dimension itself are like all the data points. So a simple way to do that is simply like flatten out your entire matrix, right? So you basically convert that 2D array to 1D array, which basically means that all arrays will be concatenated one among the others. So I'll tell you how to do that. For now, that is what I'm going to do. And n out is 10, for example. X batch is equal to next iter ANDL and X batch is equal to X batch, and I'm gonna reshape it. So to reshape anything in PyTorch, there's this function known as view, which will basically uh, reshape it to whatever size you want. And so over here, I want my pixel values to be 28 by 28 pixels rather than two dimensions of 28 and 28. And whatever remaining dimensions this are, PyTorch can actually take care of it automatically. And to represent that, you actually just put a -1 over there. All these might be really heavy concept wise, so you guys really need to like go back to this lab and like practice this again and again. Let's just look at X patch dot shape. Sorry, and out X batch. Okay. So if I pass X, if I do model X batch, will I get an output? Yep. Actually. Oh, so let's look at exactly what's happening. So the first layer had weights that were 784 times 50. So this became 16 times 784 times 784 times 50 became 16 times 50, and then 16 times 50 times 50 times 10. Uh, that became uh, 16 times 10. So that should have been the output. I'm not exactly sure why that's not coming out to be the case. Let's debug that. Not an issue. Oh, I think my return was inside the for loop, which is why this error was coming. Yep, it works well. So this is supposed to be your what do you call your neural network, all right? It's just nothing but stacked layers on top of each other, stacked weights, stacked array multiplications on top of each other. So in logistic regression model, we had weight times bias. Over here, your weight times bias, which again goes inside another weight plus bias. Another goes inside another weights plus bias, and so on and so forth. Here's one small detail that you need to take care of, and this comes from mathematics, by the way. Let's say f is a linear function, t is also a linear function, h is also a linear function, which is what essentially I'm trying to gain over here. So I have some input which goes inside the function h, which goes inside the function g, which goes inside the function g, f, and this is supposed to be an output of the neural network model. But if you think about it, a linear function of a linear function is also a linear function, right? This is a limitation of a linear function. And so, like, why would you in some wild scenario even want to stack three linear functions on top of each other when the final result is also going to be a linear function, which could have ideally be represented in only one layer. You didn't have to define three separate layers for this. You get my point? So, in order to actually overcome this, scientists actually introduce another function over here, which I'm going to name A. A. Yeah. So first X goes inside H, after which it goes through some non-linearity. So to break that linearity, because f times f of g of h is also a linear function. I don't want a linear function because there's no point of having three stacked linear function. So to break this continuity, I need to introduce a non-linear function. And the non-linear function that we usually use is known as a ReLU function. Stands for rectified linear unit. This is what it looks like, by the way. This is what it looks like. That's it. It's basically defined as if the value is less than zero, the output is zero. But if the output is greater than zero, the same value is returned. So it's defined as y is equal to x for x greater than zero, but y is equal to zero for x less than that. I mean, like any sort of non-linearity actually works, but people actually use ReLU most often. To be fair, you could have used torch.sigmoid also as a non-linearity function, and people actually used to do that sometime ago, maybe in the 90s or so. But now people only use linear function. So it's actually defined in torch.nn.relu. Let me just define relu. F relu.
Could you explain why you use the ReLU function again?
Sure. This is your neural network, by the way. It's nothing but so your logistic regression function ended over here, but neural network took it one step ahead, and what it did was that the output of this function will be fed as the input to another linear function. Do you get that?
Yes.
All right. So now here's a problem with mathematics. Uh, Let me just have a jam over here. Yeah. So let's say I have W1. Oh, damn, this is. Anyways, let's just say that your initial function was Wx plus b. Right? And I pass that into another linear function which is W1 times this value plus b1. So that is how a neural network is, right? And you can actually keep on going ahead. Is that fine? You get this?
Yeah.
Let me just expand this a bit. So this becomes W1 times W times X plus W1 times B plus B1. Is that right?
Yeah.
Which is nothing but some W times X plus some constant, which is again a linear function. So
Okay.
why
Yeah.
why did I have to define two linear functions if this could have been solved with just one linear function? Yeah. So
All right. Okay.
you're not essentially increasing the complexity of the function. You're not increasing the its ideal number of parameters, the effective number of parameters. So to do that, you need to break that. So between two linear functions, you need to introduce some sort of non-linearity in order to break that continuum. So now if I introduce some linearity over here, if this is passed into some non-linearity, right? And now if I pass it through another weight function, now this is not a linear function anymore. This is because I've passed in a non-linearity, it becomes a separate input in itself. And the output will be something like W times X for X greater than zero, but but zero if whenever X is less than zero, something like that. So now you're basic. So now the complexity has increased.
Okay.
You get the idea? You get
Yeah.
the idea?
Yeah. Thank you.
I'm just gonna define the ReLU function. ReLU function is very simple. Uh, by the way, sorry, everything should be a class, right? So class ReLU, and it's gonna go with. Oh, by the way, sorry, I'm not gonna define ReLU. It's very simple, right? It's all it does is that if x is less greater than zero, return x. If x is less than zero, return zero. I'm just gonna use the PyTorch's internal what do you call it, definition of that, which is nothing given, which is given by nn.relu.
Is there any other function we can use apart from redo to
Yeah,
reduce non-linearity?
yeah, I told you, you can use any sort of non-linearity. Let's actually look at the types of non-linearities. Types of non-linearities in neural networks. So, so there's the tanh function, which people use. Any sort of, oh yeah, here's. So there's a sigmoid function, which we used before. There is a tanh function, which goes from -1 to 1. There's this relu, which is used the most commonly. There is something known as a max out, which is nothing but like the maximum of two different values. There is something known as elu, which is an exponential linearity unit, which is nothing but when x is greater than 0 it is x, but when it is less than 0 it is defined, which is not defined as 0, it's defined as something else, some function of some exponential. And then there is a leaky relu, which is defined as the maximum of x or some factor times x. So relu is defined as maximum of 0 and x. Leaky relu is actually the zero, the part which is less than 0 is actually slightly tilted. So you can use all of these, and all of these will give you good results, but apparently relu gives you the best results. uh, nn.relu is actually a function in itself. Like, look at this. Here is the function nn.relu, and it's basically this implementation. You can look at it. uh, def forward is defined as f.relu. F.relu is actually given in nn.functional. Nn.functional is represented as f dot relu. So look at this. Result is equal to torch.relu. Okay, so now let's go to torch.relu. Okay, so it's a built-in function, but apparently, anyways, you get the idea. That's how it's gonna work. Let's actually look at some results. Torch.relu of 1 is gonna give you, sorry, tensor 1. Torch.tensor 1. It's gonna give you 1 itself. But if you give a value of -1, it's gonna give you 0. So that's how relu works, by the way. So what I'm gonna do is that I'm just in this model, right? I'm just gonna introduce some sort of non-linear this relu function. Right? This is a valid function. This is a valid model now. Remember, there is no relu at the end of the model because at the end we just want a prediction between 0 and 1, right? Or whatever value. Now let me see. Yeah, this still works. That's fine. All right. Coming to the loss value, loss function value. Uh, the loss of a multi-classification problem is actually defined is known as softmax classification. Softmax loss function, and here is how it's defined. So now, if you see, the model is gonna let's actually look at like one.
So we are using softmax for binary classification right now, right?
No, this is not binary classification anymore. This is This is classification out of 10 different classes. So like
Okay. Okay.
multi-class classification.
Okay.
So the model is going to give you 10 different outputs, right? Which are basically going to correspond to like how strongly the model thinks that a particular model belongs to one particular class, right? So if you remember in the previous one, whenever the model, so the model only knew if a particular class was one or a zero, right? And we only essentially tracked whether or not a model predicted it as one. Whenever it did predict it as one, we expected the model to give a value that is close to one. And if the value was zero or very close to zero, we used to predict that the model that it's some other class. Now in this case, you have 10 different values now, right? And so whichever is going to be the maximum value, right, which like in that case also, whichever was the maximum value, if the value was closer to one, we used to predict it as class number one. But here as well, I mean, whichever class is going to have the maximum value, that's going to be the output, class output. So for example, this class represents class zero, that's handwritten digit number zero. Class number one, class number two, class number three, class number four. So I don't know which one is the maximum. I'd say 0.26 is the maximum. So the model is actually thinking as of now, this untrained model is thinking that the actual class output is zero. That the model thinks that this handwritten digit is zero. But we actually know that it was five. We actually checked it before. But that's only because this model is untrained as of now. So how you actually train this loss is actually uses how actually define this loss is using something known as softmax, which is here's the problem with it. There are a lot of negative values as well as positive values. Now these weren't a problem in the logistic regression model because the logistic regression model had values only between 0 and 1 because of that torch.sigmoid function, which we have not defined over here. To do that over here, to first convert it into a positive continuous function, we first take the exponential of that loss function. And then later on, what the softmax, and each value is also normalized in itself. So, by the way, let me just show you what exactly is happening. So this is exactly what the softmax logs function is, and you're gonna learn in class why this is. Essentially, each output is passed in through an exponential function to first make it positive, and then it is normalized by dividing it by the sum of all the exponentials. So you're gonna have values between 0 and 1 now. You get that? So in that case, we use the sigmoid function to bring it between 0 and 1. In this case, we use this normalization of exponential functions. And then we're gonna pass it through a log function. And what this does is because exponential values are very hard to handle, because exponential values can become large very fast. So you take a log of that value. Yeah. And then you basically see that wherever the value is maximum for that log function, that is the output prediction, basically. So that is how this loss function is defined. So I'm just going to define this very fast. Now there's a problem with this. I can actually simplify this. So if I actually simplify this using some law of mathematics, I can just simply do log of e to the power fyi minus log of the sum of all the exponentials. And so the first term is just going to cancel out each other, right? Log and exponential are going to cancel out each other. So I'm just going to calculate that using that sleek trick. I'm just going to define a class over here. Def log of sum of exponential, which is going to be the denominator term. That's going to be, and by the way, that also has a problem. So the correct way to do that is to not actually first calculate the sum of exponentials and then do the log. I'll tell you why. Because exponentials become big very fast, and when you add different values, it can blow up very fast, and like CPUs can handle very big values. So the correct way to do that is to first find the order of magnitude. Is to first find the order of magnitude and divide the entire exponential terms by that order of magnitude. So you actually normalize that term also. And later on, because we know that, like, how do you actually, like, how do log like, if you remember the properties of log, if you take out the order of magnitude and take it out separately in the power, you can bring it out of the log term, right? And then you can later on bring it back inside the log term. So that's exactly what I'm going to do. uh, m is equal to x dot max in the last dimension. Just follow me and you can understand what's exactly going on later. What values? M is going to give me the order of magnitude of the largest exponential term in this. So what I'm going to do now is that first I'm going to take it out of the log value, and then I'm going to later on add it on later on. So it's basically x minus m dot exponential. So I'm taking the exponential of every term minus the order of magnitude. So I'm first, so in log terms, I'm basically dividing each term by a certain factor, and then taking the exponential just to make sure that the value doesn't explode later. Right? And that I need to do a sum of that over the last dimension again. Okay, so the denominator term is done. Now what I need to do is I need to define the numerator term also. So log of numerator divided by denominator is nothing but, I mean, log of a by b is given by what? Log a minus log b. By the way, let me just insert this image over here. Um, so we're actually wrapping up this part very fast. Anyways, so, oh, I'm sorry, just a second. I'm gonna put in the loss function over here, and you can access it whenever you want. So this is log a minus log b, right? And so uh, what becomes log of e to the power fyi divided by the negative log? Sorry, that's sum of logs. It simply becomes f negative loss log loss. But why negative? I don't negative actually because there is a reason for that, and you learn it in class. There is a negative sign over here, and then there's the log value itself. And the log of exponential of the numerator is just going to cancel out each other, so you're just going to have what do you call the term itself without the exponential. So it's going to be return x minus log some x. All right. So by the way, this is known as log softmax. I'm just renaming this for better. So this term is known as the softmax terms. I've calculated this as of now. And then I need to calculate this over here, which is nothing but like whatever. So you only consider the ground truth, the log of the term corresponding to the ground truth value. You don't consider the loss of anything else. And that's the same as in our logistic regression as well. I mean, like we simply didn't consider whenever the target value was one, we only considered one particular value and we scrapped out everything else. So similarly over here, we also scrap out everything else except then the term which is corresponding to the term of your ground truth. So that's going to be my final term, def negative log loss. And it's going to take in both the prediction and the target. And I'm going to have log softmax prediction equal to log softmax prediction. I'm going to pass in the prediction, and I'm going to just do return negative log log sm spread. But it has going to have 10 values, but I'm only going to choose that particular value which is corresponding to the actual target value. So just copy. Here is a very clever trick that you should know. Whenever you want to index a tensor, a PyTorch tensor, right? You can basically give it an iterator that go from 0th to the last index, but only choose. But even within those indexes, only choose. So, like for example, let me. So, for example, if this only choose. Okay, sorry. Choose a particular value out of this tensor, which is given by this particular array of arrays. So this is basically a 2D array, basically containing rows contain data points, and the columns contain the data point and the features of the classes. And basically, my model is what uh, this type of indexing basically tells me. Where I'm doing a square bracket, where I'm doing square brackets, and then square brackets have two different terms. The first is an iterator. The second one is a conditional checker, which is basically going to tell PyTorch that go inside this target value, then let's say the first value is 0. So out of the first array of this particular item, it's only going to choose the 0th element. If the second value within the target array is 4, it's going to go inside the second row inside this thing, and it's only going to choose the fourth element. And that is how it works. Yeah, it's a very sleek trick. You should actually revise this. It's a very sleek trick to do this, guys. So yeah, I defined the loss function, and remaining all is actually the same. So I'm just going to copy the learner class here for a second. My learner class is over here. So let's just go from top to bottom. Train DL, valid DL, model, blah blah blah. Okay. F, blah blah blah. Yep, it works. But I need to do one small thing over here. That is, let's look at X batch for a second. Oh, not X batch. The default shape of any batch is actually 16 times 1 times 28 and 28. And every time I actually have to convert it into a particular shape of 21 times 28 by 28 times. That is 764 pixels. Because that's what my neural network takes in as input, right? It does not understand 2D inputs, 2D arrays as inputs. It understands only 1D array as inputs. So before actually making the predictions, I'm just going to go and do X batch is equal to Mnist pre-process batch. And similarly for validation as well. I think that should work. And now I'm going to define Mnist pre-process function over here, which I'm going to do separately, by the way. So f Mnist pre-process, going to take an input, and all it's going to do is x is gonna become x dot view minus 1 comma 28 times 28, right? And you can also optionally also normalize these values. So uh, normalization is actually a very standard thing that you're supposed to do always. We also did it in the last time in the logistic regression class, if you remember. So I'm just going to use the torch.nl.functional.normalize x. I'm going to return x. Accuracy needs to be changed to. So by the way, uh, loss fn has changed. Accuracy has changed as well. So I need to define my accuracy because it's not the binary classification anymore. So it's going to take a prediction, it's going to take a target. It's basically going to say that basically give me the maximum prediction that the model gives. So for example, this is the output that I have, and I'm basically going to say that since 0.26 is the maximum value that the model predicts out of all these 10 values, my model actually, I'm going to say that the model predicts the answer as class number 0. So for that, I'm just going to simply type torch.argmax, which is basically means that give me the value whose value is the maximum. Right? But dimension is 1, is the first dimension because the 0 dimension is the rows itself. Outfloat, mean. Guys, I actually understand that this is really heavy concept wise. So you need to actually go back and revise this within the next 2 weeks. I'll put in a reminder on the group, by the way. But so that is a definition of accuracy. I'm just gonna put it over here. Right? But I hope this works. I'm just gonna go learner is equal to deep learner. Same stuff. NDL, RTL. What else? Model. Uh, Optimizer. I have not defined optimizer. Have I? Oh, I haven't defined optimizer, so I'm just gonna copy the code. Sorry, I'm just gonna copy the code of the optimizer from here. Right. Uh, Optimizer is equal to optim, and loss fn is equal to this loss that I've defined over here. That is NLL, right? All right. Does it actually work? Let's see. Learner.fit. There is some invalid syntax. So in the definition of accuracy, this is some. sorry, misplacing of brackets. Hope this works. Invalid syntax again. Uh, do any one of you see any kind of error? Oh, self-dot accuracy. Oh, return. Invalid syntax. Uh,
I don't think we need to mention dim equals 1. We can
no,
just put
but
1.
no, dimension is equal to zero is the rows, right? So it's going to calculate across all the rows. But we actually want the argument, the maximum argument across each row, like across the 10 predictions of a single row.
Okay.
I'm just trying to see why does it show me an error. Oh, the error is over here. There was no error over here. Anyways, valid DL, so it's test DL. Sorry. Optimizer is not callable. Uh, okay. Okay. I need to give it the function itself. Yeah, I think it's working now. Okay. Dark. Okay. Dark. Target. Yep. It's kind of working. So now let me just run it for 10 epochs, let's say, and let's see where it goes. Right. 9.79%. Uh, it's not increasing.
Would using pre-trained weights help? Like from
Sorry, can you repeat?
I'm saying, would using pre-trained weights help?
I don't really think there are pre-trained weights for this particular. No, you don't need pre-trained weights for this. You'll see. You'll see.
What if we take some lower level feature from some bigger model and then put it here? I don't know the syntax and all, but would it work
Yeah, but
theoretically?
yeah, I mean, why not? It would theoretically work. But like, why do you want to jump like so far ahead? It's. I mean, like for small neural networks, you actually shouldn't you actually even use pre-trained weights. So I have an 8.9% accuracy. I hope this increases. I think there is some error. And so we'll try to. I'll just stop at this point. I think it's not worth. So we'll continue this next time. And so what we actually learned today, we actually learned a lot of things today. We actually learned how to construct a multi-layer perceptron. We actually finished. We actually learned how to factor our code into really good classes. And as a good exercise, you guys can try to see like why it's actually not improving. I'm making some error myself. I get it. And so either I'll solve this on my own time and I'll put up a small note like what exact changes need to be done in order for this to work, or or you guys can actually do it on your own and tell me, put up a message for me that this is what actually was wrong and this is how you're supposed to work to make it work. So I hope that. So I'll see you guys next time, and next time we're gonna start with computer vision, and that's actually a really important part, like one of the most developed parts of deep learning, I'd say, and really exciting as well. So I'll see you guys next to next week. And so if you guys have any question, I'm over here for some time. Until then, I'm actually trying to debug it myself.
So I had a doubt in the previous lab.
Sure.
Um, let's see. So there's a function named train one iteration, and that's where you set the gradients as none. So is that similar to what we did by in the step function where we put with no grad?
No. So torch.nograd is different from zero grad. So zero grad actually replaces the gradients with a value zero. Okay.
Yes.
Torch.nograd simply tells PyTorch that do not calculate the gradients with respect to this step. Ignore the gradients. Ignore calculation of gradients corresponding to this particular operation.
Okay, and why do we do that?
So, I think I already explained this to Prabhav, but I'll explain this to you once more.
Oh, yeah, I didn't really get it that time.
Sure. Do you notice how we have not calculated? So, do you understand that we need gradients in order to train a model? And
Yes.
why do we need those gradients?
Yeah, so we can reach the optimum parameters.
Right. So we actually saw how that is done using I don't know, was that we learned about gradient descent, right?
Yeah.
So we actually come down and down. We come to a global minima using gradients. Yes. We actually don't calculate gradients manually, and we let PyTorch do that for us. Yeah. So how do you think that PyTorch actually keeps track of like what operations to take gradients with respect to, or like what how to take gradients? So can you like take a guess like how PyTorch does that?
So I think with every change in params.data, it would change the gradient value.
No, but like see how exactly. So first you need to take an x and you pass it through those parameters. Then you pass it through the loss function, you get a loss, and then you take the gradients. So
Yes.
like, and how do you take the gradients? You first take the gradient of the loss with respect to each parameter, and then you come back and then you take the gradient of the weights with respect to the gradient, and then you update the weights with respect to those gradients, right?
Yes.
Yeah. So how do you think PyTorch keeps track of like and like in the multi-layered perceptron case, by the way, now I have two layers. So like it will first uh, calculate the loss. It will calculate the gradients with respect to the loss, then the previous weight, then the previous weight as well. So like how does it keep track of like which operation to take loss, sorry, gradients with respect? Can you like take a guess?
It probably does for every operation then.
You mean that required gradients function that we put there and tell it to store it somewhere else?
I mean, like, no, yeah, but like, no, I'm not asking that. That is just to make sure that the gradients that PyTorch that those tensors have gradient feature enabled in them. Right? Like, how do you think that like the but PyTorch knows that which functions to take gradients with respect to and which functions not to take with respect to? I'm asking that.
I guess it probably doesn't know. I think it does for all.
Exactly, exactly. So we need to make and I'll tell you like how it keeps track of things. So basically when you have x and you pass it through something, right, and if x has and you pass it through something which has gradients enabled, so PyTorch is going to store it in some memory that this operation was done with respect to the input tensor x, all right. And then when you pass that to some another function as well, it's going to store that, well, I see that this user has actually passed this particular value to this function as well. So it's going to keep track of all those things, and it's just going to go in the reverse order and calculate the gradients for all of them, right? Now here's the problem. PyTorch will keep track of all the operations that you do with your data, right?
Yeah.
Hello? Yeah. Did you get
Yes.
that?
Yeah.
Yeah. So, what is it? Where is it? Where is it? Yeah. Uh, where is torch.movement? Yeah. So this is also an operation, by the way. This is an operation in which you update the parameters of the step, update the steps. Update the values of the parameters, right? But this is not part of the model, and the gradients are not supposed to be calculated with respect to this step.
Okay.
Yeah, but PyTorch doesn't know that. And so PyTorch is going to keep track of this operation as well, and the next time you're going to calculate the gradients, it's going to keep track of this operation. It's going to calculate the gradients with respect to this step also, which is wrong.
Okay. Okay. So
So
when we're using the backward function, PyTorch will know which gradients to consider, right?
yeah, yeah, it will. It will. So
Um,
basically, just as I told you, like for example, you have x is passed into a linear function and then passed into a ReLU function and then passed into another linear function, for example. So whenever you pass x through that linear function and that ReLU function and that another linear function, it's going to keep track that x was first passed into this function at this memory location, then this memory location, and then this function. And then when you say dot backward, it's just going to go through them in reverse order and it's going to calculate the gradients step by step.
oh, okay.
Yeah, but I mean, this is also an operation that you do with your data, and PyTorch is going to keep track of this.
All
But
right.
we don't want that, and so I'm going to tell PyTorch that for this particular step, please don't consider gradients. Please don't keep track of this operation. And that's what torch.movement
So
does.
if we did keep track of this gradient, then so when backward is called, it would have considered this gradient also, right?
Yes, exactly, which is wrong.
Okay.
Yeah.
All right. Thank you.
All right. Is there anything else?
So for this week, we basically try to implement MNIST using neural networks, right? So,
using neural networks. Yeah.
so,
And
so,
actually,
as you were saying,
yeah, no, you said, tell me.
I was asking like, so do we still need to revise logistic regression or like leave that part?
No, obviously you have to,
Okay,
because I mean that's very important.
okay,
But that basically the neural networks that we've done today are just extensions of the neural network, the logistic regression model.
okay,
So it's very important to actually understand those that phenomenon. Yeah, and I'll put up a note. I think by today itself, like where exactly I'm going wrong in this particular model today. I would have sat and like debugged it, but it's very late already, and so I don't want to like take any more time.
okay. For
Yeah.
more insight into PyTorch, like is how should we go about it? Like for example, do you find somewhere something or somewhere where you were able to go back for reference and learn the proper thing in PyTorch? Like currently I'm trying it with FastAI, but it's a it's a higher level thing, so it's not as
Py,
complex as.
PyTorch documentation is like everything you need. They have
Okay,
everything over there. And
okay.
actually, you I think you mentioned about the PyTorch book as well.
Yeah,
The
so like
PyTorch.
the weights and biases are
No,
having that second reading group for PyTorch.
no, I'm not talking about this reading group.
Okay, okay,
But
okay.
that book itself is a good read. I mean, like if you want to learn about some methods, I mean, it's a good way to understand like deep learning from using PyTorch from scratch. So it actually provides a lot of good tutorials.
Okay.
You should. Yeah, it's a very good book. It's a must-have book, I'd say, for every computer scientist.
Okay. So at this point, you would still say that doing both the frameworks hand in hand would be helpful, like because FastAI is still based on PyTorch, so that
What two
syntax and
frameworks?
all would come help handy.
What two frameworks? Hello.
Hello?
What two frameworks are you talking about?
No, no, I'm asking like if I'm doing the FastAI framework, then doing PyTorch along with it would be helpful, right?
Yeah, but I'm not gonna advocate anything for or against fast AI at this point. Because well, I mean like I'd say yes to you. I mean like it's a good idea to do that. Though like in this particular lab we'll try to do everything from scratch, and actually next week I'll actually see if I'd like to integrate fast AI into this as well. But yeah, it's a good idea to learn PyTorch side by side. PyTorch is a like really helpful language, and it's really flexible in every possible way.
Okay,
So yeah, so if you really want to go beyond, sorry, if you really want to go beyond like fast AI, you'll have to learn PyTorch.
okay. Also, while replicating the notebooks, we can experiment with the other types of functions like rectified, relu, and tan.
Absolutely, absolutely. You're free to do anything.
Thank you.
All right, take care. Bye.